Inviting me to talk. So I'll be in the seminar. I'll be majorly focusing on all the kind of aspects that I worked on baryogenesis, and specifically at the end of the talk, I'll be focusing on how, in a way, how we can see the scale of the leptogenesis in gravitational wave also. So these are the research areas that I've worked till now. And specifically, I'll be focusing on these two in this talk. So the outline is, so there are three parts. So the part one, I'll be basically addressing the reinterpretation of chemical potential in spontaneous baryogenesis. Then I'll conclude, and then in part two, which will be a bit longer in a way, will comprise of some subtleties in the asymmetry, specifically the baryon number violating coupling to the right of the cut. What do we mean by that? And then realizing an asymmetry with only one L violating coupling, which is quite unusual, but you can do it, which is another kind of a clause in Sakharov's condition. Basically, that's basically coming from the Nanopoulos-Weinberg theorem, actually. And then the realization of auto equilibrium at low scale physics, right? How you can do a low scale baryogenesis in that. And then a new mechanism that we came up with recently. And then part three will be a gravitational wave and leptogenesis, how we can realize it. It will be obviously concentrating on conformal B-L model and the connection between leptogenesis and gravitational wave data. Now, we all know that there is something rather than nothing. And SAND model, however, unfortunately, it has the capacity to explain it, but the data shows that it's not capable of doing it because of the CP violation controllers. Are also very interested to understand this -20, sorry, this horrendously small. And the Higgs mass basically tells us that the first order phase transition is not, the phase transition is not strongly first order in SAND model. And these two basically, annihilates or demolishes all the possibilities that you can realize asymmetry. So we know that the asymmetry, which is number density of baryon antibaryon to the number of photon, is of the order -9. And we need a new scenario, or basically a BSM model to explain it. Be it a mechanism, be it something, but we need something beyond what we have right now. Now, there are many kinds of asymmetry or many kinds of mechanisms why you can do asymmetry. First, which is the very generic, the decay and scattering. Then we have baryogenesis by electroweak phase transition, where SAND model is part of this kind of mechanism. And then we have spontaneous baryogenesis, which is quite interesting, but it's another way. And then we have others like gravitational baryogenesis and Plausible. I'll not be touching on the last part because it's kind of very vast in a way. So in this, I'll be touching upon the first and the third one. Now comes part one. So the part one basically comprises of spontaneous baryogenesis. Now, it has quite interesting in the sense that it has some special features. A, it does not require CP violation, which is quite unusual, but yes, it does not require CP violation. And B, it is realized in thermal equilibrium. Usually when you do a Sakharov condition, which I'll write, you actually need an auto equilibrium mechanism. But in spontaneous baryogenesis, you realize it in thermal equilibrium. So it's quite a different setup. So primarily, the source term is actually this current, del mu theta, J mu, where theta usually comprises of a pseudo-Nambu-Gaussian boson of a broken symmetry. Now, assuming this theta is spatially homogeneous, then the temporal part is actually given by this. Now, this thing, specifically, naively, we say that actually it splits the energies of particle and antiparticle, hence gives the asymmetry. Here we kind of differ. So this is the entire, so this is the main talk now is countering that idea that it's not CPT violation. That's the whole point. So usually they say that this theta dot is actually interpreted as the equivalent of energy splitting. And what we are claiming that is not, oh, okay. But does it? No, it obviously it's not. Yeah. So we say that it's not necessarily implying a splitting, but the point is not that it does not give asymmetry. That's not the point. The point it does give asymmetry, but the interpretation is different. Oh, sorry. And we also argue that the dispersion relation when you expand the Fock space of the field, the dispersion relation of the K naught that we see there, it does not necessarily represents the energy of the particle and the antiparticle. And spontaneous baryogenesis model also considers rapidly oscillating fields, which we are not kind of addressing right here. Now, to extract the energy of the particles, what we actually have to do is to obtain the Hamiltonian, take its expectation value. The expression will not necessarily agree with the K naught that you get. And in particular, K naught may contain theta dot, the single particle and particle may not. So let's start off with an example. So we are starting off with a Lagrangian term with del mu J mu theta psi. So the Lagrangian looks like this. And here, this theta, as I explained, that is part of some pseudo-Nambu-Goldstone boson of some broken symmetry. Now in the literature, this kind of becomes like this. There's difference. And which is interpreted as giving a splitting. So let us, I'm sorry. So let me just go back a little. So let me just start off with this. So So if you expand the field in Fock space, so usually what this Ft and Gt, what you do, you put it in terms of your equation of motion, basically Euler-Lagrange equation, and then you get the Hamiltonian, and then you interpret this K naught as the energies. So let's do that with the Lagrangian that I've mentioned right now. So what you find, so this is the equation of motion that you get, and then we do when you multiply from the left with this, you get this solution where this F, you'll see it has a different function. Now this K naught U is basically E star plus theta dot. Here, the energy, this dispersion energy is not actually the energy of the particle and particle. This E star is actually. Now, when you go down and do for the negative energy, you get another solution. And then, how do you know? So what you do, you basically plug it in, and you solve for the U and the V's, and then again you go for and solve for the B, the D. Doing the entire second quantization and the first quantization, and then you put it back. So you calculate the normalization with this, and then you calculate the Hamiltonian. Now, that's not all, where you see still here that you actually have the theta term. What you do, you actually calculate the time-ordered Hamiltonian from this. And when you do that, what you'll see that you're actually getting no difference. So this is actually the solution for this. So you do not get any splitting when you do the time-ordered Hamiltonian. So what does this tell us? It tells us that the theta dot term, what it does, it distorts your mode function. And your particle-antiparticle energies actually is not splitting. What it does gives you an effective chemical potential. So the interpretation is that it's not violating symmetry, but it's actually giving you the breaking of the symmetry is actually giving you an effective chemical potential, which basically gives you the tilt or the difference. Now let's go back and reanalyze how it is giving the asymmetry. So we went back and we calculated the asymmetry or the Boltzmann equation, taking the Lagrangian from this paper. And we did the same calculation here. What we found out, when you calculate this and you put back, you do the rotation and you put back the mode functions here. So in the Boltzmann equation, you put back the Boltzmann equation in this K naughts, which is here. And then what you do get is this. So where the dispersion, the distribution function is this, you put back all the K naughts, you get this. So in this, you'll see when you satisfy this relation, you're actually getting this. And when you put it back, you're getting this theta dot. And then you're actually, when you expand this, you're actually getting the theta dot. So what is happening is that your effective chemical potential is actually giving you the asymmetry. So what we got from here, we saw that in equilibrium, you are getting an asymmetry. It's not, we are not stating that you're not getting any asymmetry. You are getting the same asymmetry what they got. But the interpretation is different. That's the entire bottom line of this. So you go back and you do the same thing, something similar in the scalar field. You do the entire calculation again. And you do the first and the second quantization. You see that the energy is again redefined, like it's basically is this. And then you go back and do the Boltzmann equation, go back to the Boltzmann equation, and you see the same. You're getting an asymmetry, but there is no splitting. But there are some Lagrangians where you do get a splitting. Now those Lagrangians are quite unusual. So if you, like, we took the Lagrangian from this paper, which is something like this, it's kind of a magnetic field kind of term. And when you do the same kind of calculations here, you will actually find that there is a splitting. Sorry. Yes. Yes, this epsilon ij is kind of a magnetic field kind of thing. So, okay, to be very honest, this paper that we did the calculation with, so this paper said that the primordial magnetic field kind of gives a splitting or whatever. It is a reason for asymmetry, and they took this kind of Lagrangian, which, okay, I don't like. It's like it's a string-inspired Lagrangian. So we said that, okay, let's do this the set of calculations which we did for the first two Lagrangians, which we understand, and then we find out that although it does, like, from look at the Lagrangian, you would say that, okay, it splits the energy of or particle and particle. We found out that it does actually, in reality, it does, because if you do all the first and second quantization and take the time-ordered Hamiltonian, you will see that there is a splitting. When you do the time-ordered Hamiltonian, you'll actually see that for the particle and antiparticle, you are actually getting a different energy sitting in front of them. So, yes, exactly. So what's the lesson that we get? So when we are dealing with the spontaneous baryogenesis scenario, you really need to do the entire calculation as to see till the time-ordered Hamiltonian, are you getting a splitting or not? And then basically the interpretation comes from there. So the conclusion is that it's like, basically the conclusion is two-part. Whether or not the term of the Lagrangian gives rise to energy splitting or not. That's the first. Are you really getting an energy splitting? B, are you actually doing an asymmetry or not? Because the splitting might, you're not certain that it's giving you asymmetry or not. So these are the two things that you need to be very careful when you're dealing with spontaneous baryogenesis. And then, now for both Fermion and scalar, we do find the term theta dot j naught modifies the mode function. There's no splitting the energy. but it is actually giving you a matter-antimatter asymmetry. So what the thing is, it actually creates an effective chemical potential. So you can imagine in a way that when you are breaking some global symmetry, that thing is actually creating an effective chemical potential, which basically disbalances the matter-antimatter asymmetry. Yes.
So could you actually explain that in, again, like how the chemical potential is manifested from that?
How the chemical? How
yeah,
it is
I kind of missed that technical.
Yeah. So the point so do you want to see the equations again?
Yeah.
Okay.
Show that one more time.
Let me go to the fermionic part, which is so when you start off with this, so you actually I'm sorry, this ordering. So this is a scenario where you say you start off with where there's no theta. Okay. So when there's no theta, you start off with this, you'll find out that this ft, you just treat it as ft and g of t. What you'll find when you calculate with the equation of motion, this kind of turns out to be like this, which is a standard one that we know. And then you identify the k naught with the energy of the particle antiparticle. Now you go back and put back the theta term. And these are the equation of motions that you get with the theta dot terms. Okay. Now again, you do the way you do, you multiply with the plus sign, and then you get this, and you solve for f dot by f, and then you get this expression. Now this mode function is now you see this extra theta dot has a rise. Okay. And here also the theta dot has a rise. Now the point is.
That looks like a chemical potential.
Yes, this theta dot is actually the chemical potential that is there. So that is coming from the symmetry which this particle is associated with. Okay. Now, how do I know that E star is the energy? So what you do, you go and put back and you solve for the particle, the spine is the U and V, and then you get this thing and you have the standard normalization sitting in front. Then you go and solve for the normalization. So you calculate the second quantization you do, you calculate the B and D, and then from there, you actually get these normalizations. Okay. And then you calculate the Hamiltonian from this. So when you get this Hamiltonian and you calculate the time-ordered Hamiltonian, you actually get this.
I see. And that in that k squared plus m, the chemical.
This k squared plus m squared is actually the E star squared.
With the theta inside.
No, this is just E star.
Oh, okay.
This is just E star. The F has a theta dot. The F has an E star plus theta dot and minus theta dot.
I see. So its distribution function has this chemical.
Yes, the distribution function has it, but the particle-antiparticle energies are not different.
Okay. That makes more sense. Yeah.
Yes.
Yeah.
So it's not CPT violating, or it's not the energies of the particle-antiparticle. No, it's actually effectively creating the distribution function such that there is a split in the distribution function. But the particle-antiparticle energies are the same. That's the point.
This is all classical levels. Anything change? Blue Porter. I mean,
No. So that's
the reason I'm asking is if you're using these equations of motion, I just worry about if you have like triangle anomalies or something.
No.
When you're coupling to these currents, for example.
Yes. So basically, you're starting off with some, let's say, some global symmetry, and then you're doing the calculation, taking that field as a background field, and you're doing the calculation with that. So the point, so when you do the loop correction, this basically you're doing some interaction loop correction with it. So here you're taking that field in the background and doing it along with it. So okay, so let me just skip that. Done. I'm sorry. Let me just skip. So yeah. So okay. So yeah. So the conclusion is it's not necessarily splits, and then the theta dot j naught in the Hamiltonian does not implies a splitting. So that's again and again I'm just implying this. And we also studied the case where the field derivatives are replaced with G2, which was a very special case that we have seen at the last. But that term really splits it, and you really need to come down to the time-ordered Hamiltonian to see that. Now, coming to part 2, which is basically concerning asymmetry coming from decay and scattering. So here, you need to consider Sakharov's conditions. So Sakharov conditions is A, you need to have a baryon number violation in your theory. B, you need to have C and CP violation. Basically, you need this difference in your decay rate. And C, you need a departure from your thermal equilibrium. Having said that, there are two very subtle points along with this that you need to be very careful about. And those 2 points is that, okay, I'm sorry, I'm running. So let me just give a very brief tour what leptogenesis or whatever from decay and inverse decay is. So let's take a case of a scottogenic model where this term is actually gives you, the decay term is actually gives you the asymmetry. And this is the decay from where you're getting an asymmetry. And the C and CP is actually coming from the loops. So these are the 2 loops that you get. So let me just, I'll address it again. So let me just mention it here. To get a CP violation, primarily, you need actually more than 1 sub-processes. However, for here, you are kind of abundant with 2 more. But the interference between the 2 sub-processes is the key to the CP violation. And actually, you'll see that in any other, I guess, any other process also, like KK bar or something else, where you have an interference term in that. So the vertex one was the first one addressed by Fukugita Yanagita, and this was by Louis and Segre. And this is the asymmetry, what you calculate, where the top one is a CP violation interference term, and the bottom one is the total width. And this is how your asymmetry looks like. And this is basically coming purely from the loop. And the first one obviously comes from the coupling. Now, let me come back to the subtleties. So the first subtlety was addressed by Nanopoulos and Weinberg. It's called Nanopoulos-Weinberg theorem. Is that to realize an asymmetry, you need at least 2 biviolating coupling in your theory or in the loop. Now, this is a caveat. You can actually do away with 1. But the caveat is that if you do not have, say, okay, the online guys can't see it. So, okay, I can do this so that the online guys can also see it. Let me just do this. Sorry. So, okay, I can do it right here. So if you have X, which basically goes to B, right? So this is basically a B violating thing, B violating decay, right? Now, say you do not have any other process other than this, then you need at least 2 B violating coupling. But say you have another decay, which is basically something else, something X bar or X tilde, which is not B violating. Then you can actually do away with only 1. That is Nanopoulos-Weinberg theorem, right? So, but then the follow-up question comes. Say you have 2 B violating coupling or 1, where to keep it in the loop. Now that's the point where the cut comes. You have to keep it to the right of the cut. What does that mean? So let's go forward. It's basically I'll be explaining this paper where you do it's a very simple quantum mechanical calculation. So I'll just briefly go through it. So it does say that you say you have process X goes to B and X bar goes to F, then you by CPT you can write this amplitude like this. They're basically in and out, and this is also in and out can be like this. So say you start off with X going to F. Okay, then you incorporate all the states or whatever, all the states here, and then you do some quantum mechanical massage, where what you'll find out is a very simple way. I would urge the students to go through. It's hardly a 3-4 papers quantum mechanical thing, and you can really do it. It's really fun, but it has really good implications. So this is the thing where you see that you get the other process, the antiparticle process, and this is actually what you need, the difference. So what you get out of it is this, where this AC that you see, when you just simplify it, you get actually this. So what does this say? It says that all the intermediate processes where the G goes to F, that has to violate B. Okay, so diagrammatically, what it actually means is that, say you have an X goes to F. Okay, then you have these two processes where you have a B violation to the right of the path. That G goes to F is basically from left to right. So all the processes which basically violates the B from the right of the cut, they will actually give you the asymmetry. Okay? But if you have something like this, you'll see it has all the right things, but it actually will not give you the asymmetry. It has a B violation here, but somehow you're doing it like this. It will not give you the B violation. So to be very honest, I can draw a very simple diagram. You guys can all, okay, let me just do that. No, the guys in the online will not see it. So say you have simple leptogenesis. So you have an N goes to L and H, right? I can always have a diagram like this, right? But this does not give you asymmetry, right? The only thing that gives you asymmetry is this. Where this is actually the right of the cut, where this is N. Okay, so this is it's very subtle point. Like in leptogenesis, it's very trivially satisfied, but people have not seen that, the L also gives a photon or whatever, a Hamilton charge. That's also there, but it doesn't give. So if you do some summation over all the inner states, you'll actually see it doesn't give it. Right? Now let's go back and see how you can realize with only one B violating coupling. So, sorry. So yeah. So if you have, that's what I've said, if you have a process other than the B violating decay, then you can actually do away with only one. So let us see how we can do that. So let's, okay. Now I'll actually go step by step, is that how the right of the cut is very important. And then I'll go with the work where we have shown that only one B violating coupling you can do away with. So let's go some very trivial or very simple criteria of leptogenesis. So for R2 equilibrium, this is the condition that we need. And then in this, the condition constraint of the coupling to be very tiny. And this is primarily because this condition is mediated by Planck scale. Now, in order to realize it in a TeV scale or low scale, what you actually do, the most natural way to do it is to go one step further, not to two-body decay, but to three-body decay. Now, what's the advantage to that? Is that this gamma will naturally be suppressed. What it will do is that it will be not only be suppressed by phase space, it will be suppressed by the couplings. But if you calculate the asymmetry, the epsilon, that will be still be quadratic in coupling. And that's the advantage here. So yeah, that's another way you can actually naturally come to a low scale leptogenesis scenario. And this has been really explored very extensively. Like you can do, the most obvious one that you can do is a three-body leptogenesis. Or which people which I have also explored extensively is a wimpy leptogenesis, where you have a WIMP process, and that WIMP process also gives you an asymmetry. So like the freeze out of the dark matter is not only gives you an asymmetry, it's giving you dark matter also. So now let's go back to see the application of the right of the curve. So what we have done, we basically addressed a soft leptogenesis scenario. So what is soft leptogenesis scenario? Is basically it's a mechanism in which degenerates matter-antimatter from auto equilibrium decay of heavy S neutrinos. So let me go back step by step in history. So this was the first paper where they claimed that they got an asymmetry by an order m square by n square in the vertex correction. Now, furthermore, since the Yukawa is replaced by a gauge coupling, the CP violation parameter, a large CP violation can be obtained. Okay. However, the follow-up paper comes and says that, okay, that they showed that the cancellation still holds, but if you take finite temperature, you might get something. And then the third paper comes, and then they say that, no, it's not correct, that even if you take a finite temperature, you don't get an asymmetry. Then we went back, we addressed all these papers and said that, guys, you have not taken care of very simple criteria, which is basically right of the curve. So let me explain what they did. So what they actually did, so this is the process that they considered, okay? And the guys who said that, okay, sorry, these are the two processes. And what this did is this. These are the processes that they said, like this was the first paper where they said that they got an asymmetry because here it's an SU2 coupling. It's pretty high. And obviously you can see that there's no right of the cut. So obviously it should not give. And then they came up with this. Again, there's no right of the cut. And so all these processes which was claimed by the first two papers, they obviously it was not a right of the cut. They didn't have the right. It's a simple criteria that they didn't see. So what we did, we actually went back and actually did a rigorous calculation and saw which all diagrams will actually give and which all diagram will not actually give. So if you see the diagrams here, let me just, yeah. So the three sets of diagrams that you can make, sorry, six. The first three are these, where you do not have right of the cut. Okay. Then you have these, which you actually have a right of the cut. Now, figuratively, it's basically very easy to see. Even in the calculations, if you do, for the A, B, and C, these are the processes, these are the asymmetries that you get, the epsilons that you get. Okay. And for the last three, these are the things. Now, if you sum over all the internal states, what you'll actually see is this. So all these states, if you do the summation of all internal states, the A and B and the C separately are 0, exactly 0. But for the D, E, F, the last three, which actually you see there's a right of the cut, it gives a non-zero value. So the whole point is, so when you're dealing with decays or when you're dealing with asymmetry via decay or scattering, this is a, other than Sakharov's condition, you need to be very careful as, is it really giving it or not? That's the first check. Okay. Now going to the application of B, how you can realize there's only one B violating coupling. Okay. So the scenario that we took is R parity Leptogenesis, where not the lightest, but next to lightest neutralino is given the asymmetry. And it is obvious that the next to lightest will decay to the lightest one. So that is one decay which does not has L violating coupling. And then the other one is the R parity one. And the amazing part is that the CP violation is not coming from the R parity violating coupling. It's coming from the Majorana mass, the relative Majorana mass of the neutralinos. So this is the setup where we have actually assumed the Higgs to be very heavy. It's the reason because the Higgs will actually give rise to other processes which will involve Bejinos. So we will have like the washout is pretty high in that case. So the best case is taking a bino and a bino. And this is the process. So you have the first process, which is next to lightest decaying to lightest. And then this one. And here again, you need to take care that there is a light of the cut happening. So this is a very like good check that you need to do. And there's a result. So for various parameters for this. Then coming to third, and while addressing the third, we actually stumbled upon a new mechanism. So let me just describe that. So this was the work with Bhupal and Shinkyu Kang, my collaborator. So let me just briefly go through what exactly the recipe for the asymmetry is. So say you want to have a non-zero asymmetry for X going to B. So you need at least two subprocesses, which I mentioned earlier. So let us see by calculation how you can do that. For a process for X going to F, if this is the process, then for the anti-particle, this is the thing. The thing that you'll notice is that the couplings is conjugated, not the amplitude, not the spinorial part or the amplitude of that process. So when you do the asymmetry, it's a very simple calculations. I would urge the students if they can do it. It's hardly a one-page calculation. So you'll see that there are two parts. One is purely coming from coupling, the other coming from the amplitude. Now for a decay 1 to 2, which I mentioned, the only way to get the second subprocess is to go to loop. So that's why the imaginary part of the loop, that the jargon that goes, is basically the optical or the absorptive part. Okay. Now the same thing that you can do for the 2 to 2 process is basically going for the imaginary part of the mediator, basically the Breit-Wigner propagator. So for a 2 to 2 process, you can have two different mediators. Similarly for 1 to 3. And the asymmetry for, okay, this asymmetry is basically, let's say it's for the 2 to 2 process, where this gamma and this M1 is basically giving the Breit-Wigner one. Okay. So for the 1 to 3, it's a bit tricky. If anybody is interested, I can tell you how you can do that. And this F square is the spinorial thing. Now let's go and see how you apply it. So in the minimal model, we go for a very ugly looking model, but it's still minimal. So it's a triplet scalar, and then you have 3 copies of my fermion, and there's a Lagrangian. So here, the guys who are giving you asymmetries is a trilinear coupling and these 2 guys. Okay. So the process is this. So this is the neutrino mass, where the triplet is actually giving you the type 2 seesaw, and the radiative is giving you scotogenic mass. And the process is this. So the 2 different mediator is a triplet and the right-hand neutrino. And the CP violation is actually the CP violation of the coupling is actually coming from the trilinear. We have just assumed there is no phase in the Yukawas, just to be very simplistic. And then the delta comes out to be this. So you see the amazing part is that the asymmetry actually carries the decay width of the unstable mediator. Now, the amazing part is that this decay with the same bit is basically associated with what you see in the colliders. So there is a connection that you can have. So the wimpy baryogenesis, or if you're getting an asymmetry from an unstable intermediate particle, so same decay weight you can see actually in the collider. So that's the connection that you have. So there's a Boltzmann equation. So these are the 3 washout terms. And the asymmetry kind of boils down to a very simplistic scenario. But here, since I'm talking about a wimpy leptogenesis, one has to be very careful, because there's a very simple rule that you need to be very careful about. The rule is that the washout of, or basically the washout of the leptonic part and the actual freeze out of the WIMP, that ratio has to be less than 1. Okay. Now, this was pointed out first by a paper by Lisa Randall and Jan Chui in wimpy baryogenesis. There, they satisfied this condition by assuming a heavy particle at the other end. The reason is because there, the process which is giving you, or the process which is responsible for the freeze out, is the same process which is giving you the asymmetry. So that's why, to have this ratio to be less than 1, you need the final particles to be heavy. In our case, the main washout is coming from the electroweak, eta going to W plus W minus. It's way stronger than eta going to 2 leptons. So that's easily satisfied here. So this is a kind of a result of the scan that we have for the trilinear with the wave. Now coming to the third part, which is gravitational wave, how we can see gravitational wave and leptogenesis. And this is obviously very, very model dependent part. So let me just go. So the mechanism is quite exciting. It's basically pointed out where Ian's Valdez's recent paper, where they said that the relativistic bubble is actually giving you asymmetry. So how it is doing it, that's quite interesting. Say you have a wave or some broken symmetry, which basically breaks the electron number or something, say value number or something. Now inside the bubble, and this is specifically for a conformal mode. Why? Because outside the bubble, everybody's massless. The symmetry is not broken. But inside the bubble, the symmetry is broken. Or some fermion which gets mass, that's inside the bubble. So the moment your bubble expands rapidly, that fermion, which is basically relativistic, gets mass. And the time your nucleation temperature comes, it's already out of equilibrium. So
how do you create these bubbles?
So it's basically a phase transition. So you have a first order phase transition of a conformal model.
Oh, okay. So that part is not written.
That's why.
That part is not written. Some phase transition.
No, you need a phase transition. So that
that's
and
an
it's
input to this.
yeah, so it's a supercooling phase transition. So there it's and for a supercooled phase, your bubble is primarily relativistic, right? And your so the basically your Lorentz factor has to be more than mn by Tn, right? For this to happen, actually. Now, the basic mechanism here, which I just briefly mentioned, that your Yn or the co-moving number density of the right-hand neutrino, okay, in this case, I'm taking under consideration a B minus L performance model. So the decay guy is n going to LMH. So the Yn has a relativistic number density because it's massless. And then the moment, so now provided that the Lorentz boost is more than mn by Tn, the Yn is maintained across the bubble. The Yn is actually maintained across the bubble. Now the bubble, the moment it expands, the initial condition of the Yn is actually the relativistic number density. From there, you actually do the evolution of the Boltzmann. And what you see is this. So the asymmetry is actually with ratio to the observed asymmetry. Is this, and this ratio is actually taking care of the entropy dilution, or it's basically taking account the entropy production from the reheating or the phase transition. Now you need to take care of the thermal masses also. Now this is quite subtle in the sense that although your right-hand neutrino has acquired the mass, but your Higgs and the electron will have thermal masses around that temperature, and that's quite close enough temperature. Now this, you need to be very careful that this decay, although you need to be careful that the decay although happens or not, but then what you find out that at the reheating temperature, the MH plus TH is 0.77 times reheat temperature. And your Mn at T reheating is this. Now this basically gives you two scenarios. So one scenario where your leading term, which actually comes from the pair, is less than this. And the other scenario where it is more than this. In the first scenario, you need, if you really need this scenario to happen, you need the GB minus L more than 2.2, which is quite strong enough. So basically, so Ymn is obviously the leading part for this. And we can actually parameterize Y as some factor of GB minus L. And what we find out that the washout term is this, where it is obviously it's always satisfied for the reheating temperature. And you assume a standard Casa-Separa parameterization for the Yukawa. And what you found out that your Mn comes out to 1.54 at reheating, as obviously it's always satisfied. Now the result for the gravitational wave is this. So where your signal is calculated like this. And this is what we found out. So this is the parameter space so this is the parameters which is basically ruled out in a way for all the experiments that you see. So this is basically rho greater than 10 for all the future experiments. Now the exciting part is this one, the last one. So this is basically the current LIGO Virgo running, and here this is the parameters which is already ruled out for this particular model. Yes.
So what energy scale is this happening at?
Oh, the energy scale is pretty high. It's around. Okay, you can see here.
Okay,
It's pretty high.
All right, that's what.
So
to get into the LIGO range.
Yeah. So the amazing part that what we found out that the LIGO Virgo for this particular model has already ruled out high scale leptogenesis. That's the amazing part we found out in this.
So why do you need a race?
No.
Is it like you want?
No, the point is we are okay. as I said in the earlier journal club, I'm basically masochistic. So we really want this to die.
Because the
So-
scale, I can have a low scale.
Yes, sure. That's what I showed. The low scale we can obviously have.
Escape,
But the
like-
point is, so the point is that the whole point is how can I rule out or kick out models?
No, that's fine.
So
But
this is basically, so this scenario is saying that,
LIGO is searching for that high scale, but does that high, my question, does that high scale
Huh.
have in for any other part?
triangular, the mass of the right hand neutrino.
Because that can be, like anywhere in it.
I totally agree. The whole point, that's not the point. The point is can this model, or really should we really take this model seriously or not in the future? Okay, let me put it this way. If you really look only at this model, it's not that that if I start with this model, can this be distinguished with other models? No, that's not what we are addressing. What we are addressing that if you start off with this model, is it really a reasonable model or not? That we should go forward with that.
We
So-
get a kind of signal that like,
In a way, so LIGO work has already ruled out these parameters. That means that this parameter space, and in future, we see, oh sorry. In the future experiment, we see almost all the parameter space, oh sorry. You see that most of the parameter space is actually getting ruled out in the future experiment. So, in a way of saying that this particular model will be kind of meaningless in a way. That if you're saying that in this particular model, if you want to search a gravitational wave or something, then it's actually the leptogenesis and everything, it's kind of ruled out. So you can't have leptogenesis in this. If say in the future, LIGO does not find anything, say. And then basically it says that this particular leptogenesis model is actually it's not there.
So
but cannot I have my Z prime to be 1 GeV and still have a leptogenesis model? And that can
No, let's
make
see.
a prediction and
No.
some of the
Leptogenesis model, okay. Okay, let's go one step by step. Say you're saying Z is 1G, right? Z prime is 1G. But the point is, you need the leptogenesis to happen above 100. If you're doing below 100, it doesn't, because you need the speleron to be active. See, at the end, you are looking at a baryogenesis, not a leptogenesis. So if I have,
So you need the.
so this is a basic cutoff for the leptogenesis. You need it to be above 100. Yeah, if you're looking for a baryogenesis, yes, then I'm agreeing. But that also has a cutoff. That's the QCD. Sorry, BB. Right?
Yeah, actually, I would use that suppose curve. So maybe then you are saying something. So if suppose I make predictions at Lisa or someone, your genesis is coming from baryogenesis, not from the.
Yes.
Can I make it plain?
Yes. So this, yeah.
And this is, so in these conformal theories, it's the gravitational waves are coming from the bubble collisions, you have all this energy in the
Yes.
walls.
Yes.
So, yeah, I was wondering about what controls the amplitude then of these, could you hide, well, that's what I'm wondering about is.
Yeah.
Like all
So
the-
okay. So let me put this way. So yeah. So the point is, if you're suggesting that can we have, because if you see that the trade-off is basically happening for this gauge coupling, and if you do notice that the gauge coupling is horrendously high. Usually for Z B minus L or whatever if you see the collider constant is coming -3 or -4 or something like that, it's highly constrained. Here you'll see it's horrendously high. Now this actually comes from the phase transition. This trade-off is actually coming from the phase transition. So there, if you let's go back, if I have mentioned it here somewhere, did I? No, I did not. Okay, so so basically if you calculate the action and you do get the first order phase transition actually. So that will actually require your gauge coupling to be pretty high enough. Yes.
And that's giving you this observability.
So yeah. So yeah, so these are actually my research interests, and currently I'm actually working on these. Yeah, primary magnetic field is, I'm horrendously interested in it, but let me get a job first. So.
But your model can also give rise to.
Yes. Yes, 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 but I need to study that. So. Yes, I know. So I need to
So
study
then
that.
you can have another.
Exactly. Exactly. And then we can kick that out also. I'm, you know, I'm just,
Well, depends, like
Yes.
any of these carriers.
yes,
It depends on what scale, what mass those are.
What mass?
yes,
You have this lower bound cutoff.
Right.
yeah.
I don't know, like what the.
I don't know what the
size
scale
of the conversion is. So it's an interesting question.
Yes,
So what's the
because
size of
primary
the
magnetic, yeah,
conversion?
that's still, exactly. That's still, yeah. I'm interested in studying that actually.
And then you can make a prediction.
Inflation, I already told in the journal club.
Okay.
Questions?
Yeah, questions?
Oh, there's a follow-up of work which I'm kind of really excited about, which is basically a spontaneous cogenesis that we. So it's where usually in spontaneous baryogenesis, what you actually do consider is that the theta dot, that term, you basically fix from a baryon asymmetry. That okay, you assume that this theta dot should be there. Yeah. What we are doing here, we are dynamically creating a theta dot and asymmetry from a breaking of some, let's say, a global U1L. And they basically, this cogenesis is actually giving you an axion and
Yeah, actually,
the
that's
asymmetry.
a kind of a natural thing, right? Like
Yes.
if you do it here, these the PNGB.
Yes.
You can.
Yes. And we basically arrived at that point. So we are kind of
So.
in the way of writing it down.
It's
quite
the
interesting.
beginning part of your talk, I was wondering, like, what happened to
Yeah, we are working on that. Basically, we are presenting kind of a generic mechanism where you have some global symmetry which get broken, and then you actually create from that broken symmetry you actually create an axiom that and a binary or some asymmetry of that of the quantum number. So yeah.
Okay, questions?
It's nothing about leptogenesis, no questions.
I have probably many questions, but I'll.
Yeah, sure, sure. Yeah, I will love questions.
Okay, actually, yeah, maybe, is there like a simple way of thinking about why you were only getting, your leptogenesis or baryogenesis if you have the baryon, the number violating terms after the cut versus before the cut? Is it because that they're involved in the propagator of those diagrams?
Yeah, so
What is
basically, see, to be very honest, is to see is that if you see the after the cut, because what you're doing when you're doing the imaginary, when you're demanding the imaginary part, so you're actually creating those imaginary guys in between, and finally you need an asymmetry at the final state.
You're saying imaginary because the propagator terms will be imaginary.
Yes.
That's where the imaginary is.
Yes, that's where the final thing comes out.
Okay. Oh, so your point is that the number violating terms are coming from this,
The final after the whatever it goes it goes on shell, and then that's where what you're counting on. But finally, when that process goes to the final,
okay,
that
so
actually
how
should
the final
violate.
states, how the final states are talking to the stuff in between.
Yes.
That last part.
Yes, that last process, very important, yes. because if you really very closely, now you can actually go and totally see resonant leptogenesis or vanilla leptogenesis. What you'll actually see is that for the resonant leptogenesis, you'll actually have
Yeah.
this.
Yeah.
So usually you say that the minor mass violates the lepton number. So this is what is happening. This process is violating the lepton number. Similarly, if you go for the vertex one, you go this. So this is basically this violation number.
I'll probably have to work this out
Yeah.
on paper to really
Yes.
see it. That's-
So, and now basically now if you go back and see all those processes, then you will notice that that's a certain point that's there.
Okay, so any further questions? So if not, let's begin another.